This is the third video for IB Quantum Mechanics, and we're going to be looking at various models of the atom today. Now, the first one we're going to start with is called the Rutherford Model. You've probably seen this in chemistry a little bit, but basically it's the most common idea of the atom that people have in their minds. You have a small positively charged nucleus at the center that contains protons and neutrons, and you have the electrons, which are negatively charged, orbiting that nucleus. And the electrons are very small, about 0.1% the mass of a proton. And in the nuclear unit, we'll look at exactly how we know this model, or why this model makes sense, what experimental evidence leads to it. But the idea is that the electrons are attracted to the nucleus, much the same way the planets are attracted to the sun, and they orbit the nucleus, again, just like the planets orbit the sun, except instead of being held by gravity, they're held by electrostatic attraction. But there is a major problem with this model, and it was known as soon as Rutherford proposed it. And that is that according to Maxwell's equations, which had already been accepted by basically everyone in physics by that point, accelerating charges produce electromagnetic radiation. And that means that these electrons, since they're moving very, very fast and going in circles, they're accelerating, and therefore they would produce a lot of radiation, which would take away all their kinetic energy in a very small fraction of a second. In other words, the Rutherford model does not produce stable nuclei. And so we know we need something better than that. Quantum mechanics, turns out, will provide that. And now another little bit about emission and absorption spectra. If you take an atom and it gets hit by some light, it takes energy from that light, and that can cause the electron to move into a higher energy orbit. Or if the electron starts in a high energy orbit and moves into a lower energy orbit, some light will be emitted. And it's pretty easy to make an emission spectrum. We're going to do it in this class. You pass electrical current through a gas, and then you run the emitted light through a prism, and you see what frequencies of light are produced. Remember that because we know that the energy carried by the light is proportional to its frequency, if we measure the frequencies of light that are produced, we can see how much energy the electrons are losing. So this is the energy lost by the electron, which becomes a photon. And then this is the frequency of the photon. And now, a sort of strange thing happened, which is that only certain frequencies of light are emitted from a particular element. This emission spectrum is the emission spectrum for hydrogen. Hydrogen produces only 4 particular wavelengths in the visible spectrum. You could also do an absorption spectrum. You shine light into a gas, and you place a detector behind the gas. Some of the light is absorbed, but others of it passes straight through, and if you make the emission spectrum for hydrogen, it's exactly the inverse, or pardon me, an absorption spectrum for hydrogen, it is exactly the inverse of the emission spectrum. It absorbs and emits the exact same energies. And it's particular to an element. It sort of serves as the fingerprint of that element. It's really useful in a lot of chemistry analytical techniques. Now remember, we also know that the frequency of the light is proportional to its energy. So the fact that only certain frequencies of light are being emitted means that only certain amounts of energy can be absorbed or emitted. And that means the electrons are confined to just a few energy levels. The idea is if you've got energy level 0, energy level 1, energy level 2, and energy level 3. If an electron absorbs a photon, it can go to a higher energy, but only if that photon is carrying the right amount of energy. If the electron falls to a lower energy level, it will emit a photon, and that photon will have the amount of energy equal to the difference between the energy levels. And so the discrete emission spectrum and discrete absorption spectrum imply that there are discrete energy levels, and that the electron can't, for instance, gain enough energy to take it from here to here. This particular would not be allowed, and so it cannot absorb a photon with that much energy. And we use something called an energy level diagram to represent this. Each of the allowed energy is represented by lines, and then arrows indicate the transition of the electron between those lines. This right here is the energy level diagram for hydrogen. This is called, the lowest level is called the ground state. That's called n equals 1. And you also have the n equals 2 is the next highest, n equals 3, and so on. You notice that for most actual atoms, the energy levels get very, very closely spaced near the top, and they're widely spaced near the bottom. And so any possible transition is represented by a vertical line drawn between the energy levels, and the energy of the emitted photon, or the absorbed photon, is the difference between the energy levels. It's how much energy the electron gained or lost. When a photon is absorbed, the electron is kicked up to another energy level. If a photon is emitted, the electron drops to a lower energy level. So here is an example. Let's say that we have a particular atom. It has energy levels of negative 11 electron volts. Negative number means that it has to get that much energy to knock the electron loose entirely. And it's got another one at negative 4 electron volts, at negative 2.5 electron volts, and at negative 1.8 electron volts. That tells us that the energy levels that can be emitted are 7 electron volts, the difference between 11 and 2.5 is 8.5 electron volts. (9.2 electron volts). You can also go from 2.5 to negative 4, which is a 1.5 electron volt change. From 1.8 to 4, which is a 2.2 electron volt change. And from 1.8 to 2.5, which is a 0.7 electron volt range. So these 4 energy levels can produce 6 different photon energies. And what we need to do is find the wavelength associated with each of those energies. I'm just going to do the first one. I'll let you do the other ones if you want. So 7 electron volts is equal to 1.12 times 10 to the negative 18 joules, which means that, remember that the energy equals hc over lambda. So solving for lambda gives us a wavelength of 177 nanometers, which is ultraviolet. And if you'd like to, you can go ahead and calculate the wavelengths associated with these other photons. 8.5 and 9.2 electron volts will also be in the ultraviolet range. And these other ones will be either infrared or visible because they're much lower energies. Now, if you want a real challenge, you can go from the emitted photon energies to the energy levels, and that's a more interesting one to do. I'd work that on your own time. And now we come to something called the Bohr Model. This is a modification to Rutherford's, except Bohr kind of arbitrarily said that only certain orbits are allowed. Didn't explain why those orbits would be allowed, but he said only certain orbits are allowed. And the energies of those orbits are given by what's called the Rydberg equation. The energy of the nth energy level is 13.6 electron volts times 1 over n squared, where n is an integer. So the energy of the ground state is negative 13.6 electron volts. The energy of the second level is negative 13.6 electron volts times 1 over 2 squared, which is negative 3.4 electron volts, and so on. And that means that the photon frequencies that can be emitted are given by this equation. Please don't memorize this. But the frequency is 13.6 electron volts divided by Planck's constant, and then you've got the difference between the first energy level and the energy level it goes to. You do not need to memorize this equation. If instead you memorize this equation, which even that is strictly not necessary, that tells you what the energy levels are, and then you can calculate the photon frequencies associated with it. So now let's do an example. The electron in a hydrogen atom is excited from the ground state, which is n equals 1, to an energy of n equals 3. So the ground state energy is negative 13.6 electron volts. N equals 3 state has an energy of 13.6 electron volts divided by 9, 3 squared, which is 1.51 electron volts. And that means the photon energy is equal to the difference between that. And so this particular photon has an energy of 12.1 electron volts, which is 1.9 times 10 to the minus 18 joules. And the wavelength of the light is equal to hc over E. Plugging in numbers, gives us a photon wavelength of 103 nanometers, which is well into the ultraviolet range. Remember, and because it's excited from low energy to high energy, the required wavelength of that means it's absorbing a photon. Then if it falls to the n equals 2 state, it will emit a photon. I'm not going to calculate that for you. You should do that on your own. What you need to know is the difference between the Rutherford model and the Bohr model. You should know how to read an energy level diagram, and you should know how the atomic energy levels relate to the light that is emitted or absorbed.